Hello everyone, it's great hour for me to report our latest research to all of you. I'm Yuli from Xianjiao University. In this presentation, I will introduce a studies on the oversmoothing and oversquashing problems of GNN. Let's get started. Most of the existing GNN architectures are based on the MPN framework, which has achieved success in many fields. MPN processes neighbor information of a target node through two basic operations: message generation and aggregation. However, MPN has two limitations: oversmoothing and oversquashing, which make deep MPN challenges to implement. The oversmoothing issues refers to that as the number of message passings increase, the node representation becomes indistinguishable from each other. It was nothing that appropriated smoothing is helpful classification. The oversquashing issues occurs when information from distance nodes get excessively compressed, hindering the effective propagations of node feature in graph. These issues usually occur in tree-like graph and bottleneck. The following equations mathematically explain these phenomena. As R increases, the exponential decrease of leads the node green representation being insensitively to node blue. Consequently, the oversquashing issues limited the receptive field of GNNs, so that the stacking of too many layers becomes ineffective. For these two issues, researchers provided several solutions. The first strategy is graph rewriting. This method migrates oversmoothing and oversquashing by optimization the original graph structure. Technologies such as drop edge and SDRF achieve their goals by readily deleting edges and adding edges based on the curvature, respectively. In recent years, graph transformer has been a lot of progress. This method can be regarded as learning-based rewiring. Representative works are graph formers and NAG form. They rewired based on the full graph and hopwise subgraph, respectively. The main disadvantages of this method is that it distributes the orange graph structure and may lead to performance degradations. The second strategy is to enforce the separability of node representations during the message passing process through regularizations. One of the most straightforward methods is to constrain the node representations through regularizations, such as directly integers, group normals, and node normals. Additionally, methods such as gradient adaptation, aggregation, gate matchings, and modeling the relevance between propagation are employed to limit the propagation of irrelevant information. Constraining the information flow can also elevate oversmoothing. Furthermore, several physics-inspired models such as Allen-Chen's message pattern, oscillators, networks, and gradient flow provided inherent constraints. However, these regularizations may degrade performance and lack of effective solutions for oversquashing. Residual connections are used to mitigate oversmoothing, particularly initial residual connections. Recently, geometric skip connections have been proposed to tackle oversquashing. The strategy elevates oversmoothing and oversquashing, but doesn't fundamentally resolve. Here we present a novel and effective message passing scheme called multi-track message passing to solve the issue of both oversmoothing and oversquashing. Heterophily mixing exists in MPNN, and we think it's the root cause of both oversmoothing and oversquashing. Understanding these phenomena is crucial to get basic idea of multi-track message passing. Heterophily mixing refers to the mixtures of messages with different semantics in the aggregations of message passing. As shown in upper part of this figure. The message aggregation of node 2 and 3 leads to heterophily mixing, make these two nodes indistinguishable. More importantly, heterophily mixing can propagate. As shown in lower part of the figure, node 1 is spreadable in layer LE, but becomes insparities in layer L2, and oversquashings are both rooted in information loss resulting from heterophily mixing in aggregations of message passings. The basic ideas of our models is that if messages are separated and independently propagated in tracks according to their category semantics, heterophilic mixing can be prevented by avoiding heterophily mixing to ensure the semantic purity of each node. The problem of oversmoothing and oversquashing can be effectively solved. To basic idea, our proposed MTGCN consists of the following three steps. Loading. Node belongs to the same categories are expected to associated with the same track. And multi-track message passing. The message load onto the track in the first step independently, propagated and aggregated on their respective track. Acquiring the third step is acquiring the messages from corresponding track and update the node representations. It can be seen that obtaining a good node track affiliation metric is crucial for MTGCN. The node track affiliation metric F is obtained through the track prototype P and the anxious node representation H. Therefore, before get the metric F, we need to train actual models to obtain H. In practice, the actual models is a simple two-layer GCN in step C2. We calculate P based on H. The prototype P can be considered as a class of centers of each category. After that, we obtain F through product attention. Finally, we illustrate the overview of MTGCN. The detailed intuition has been mentioned before and will not to be elaborated here. Now, why does multi-track message passing bring about improvement? There are three main reasons. The first is preventing heterophily mixing. The first and foremost advantages is its ability to prevent heterophily mixing. This is a mixing of messages with different semantic during the aggregation parts, which is the root cause of both the oversmoothing and oversquashing. Multi-track message passings allows nodes of the same categories to interact exclusively, preserving the unique information with each category. The second is facilitating long-distance information flow. The second advantage is facilitation of long-distance information flow. Unlike traditional message passing neural network, where messages are fused into node features and can't pass through unless aggregation, multi-track message passings decouples messages from node representation, enabling them to flow through any node, irrespective of whether they contributed to the node feature. And the third is enhance the separation condition. Lastly, multi-track message passing enhance the separation condition, which is crucial for effective semi-supervised learning. The separation condition refers to the scenarios where nodes exchange messages within their categories, not across, reducing the error rate. And we have proved the effectiveness of MTGCN through a large number of experiments. In node classification task, MTGCN has achieved effectively performance in both semi-supervised and fully supervised setting. By addressing the oversmooth problem, MTGCN can capture long-range dependence effectively, making it suitable for heterogeneous graph. Compared to the semi-supervised setting, in multi-stage training strategies has limited benefit in the fully supervised setting because of the abundance of supervision information. MTGCN can effectively solve the issue of oversmoothing. Our experiment has shown the MTGCN maintains high and stable classification accuracies regardless of the network dips. This stand in sharp contrast to conventional GNN such as GCN and GAT, which experience a significant drop in performance at increased dips due to oversmoothing. Furthermore, we have also introduced a group distance ratio, RG, a metric for measuring the extent of oversmoothing. RG compares the intergroup distance with intragroup distance of node representations. A low RG suggests great oversmoothing. Our findings that MTGCN preserve an optimal RG ensure that node representations within across categories remain distant, even in deep network. We also united the symmetric benchmark called the tree neighbor mesh task, specifically designed to evaluate a model's ability to handle oversquashing. As shown in the figure, the task is to obtain the category of the root node. The category of the root node is guided by the leaf node, and the intermediate nodes are all red noise. And therefore, in this example, the categories of this node is C. Our result demonstration that MTGCN achieved the nearing perfect training accuracy on this task, showcase its capability to effectively capture long-range dependency and prevent the loss of information from distance node. Notably, beyond the tree dips of 5, the training accuracy of all models except MTGCN significantly decreased. The highlight being advantages of MTGCN in handling deep tree graphs, which is very challenging for other models due to oversquashing. We observed a slight decrease in MTGCN accuracies when the tree dips exit the C layers. This minor performance drop can be attributed to the high space complexity of MTGCN. In conclusion, this paper identifies heterophily mixing as a significant cause of oversmoothing and oversquashing in GNNs. To address this, we designed the multi-track graph convolutional network to avoid heterophily mixing during message passing, and we conduct extensive experiments to demonstrate the effectiveness of MTGCN in address the two areas. If you have any problems, please feel free to contact me. Thank you.